Hello everyone, my name is Han and welcome to my channel. Today we're going to take a look at Starknet, which is the L2 solution for Ethereum. So first we navigate to the Starkware website. And Starkware has a few products. Starknet is the one we're looking at, which has a programming language called Cairo. So we go through the Cairo documentation, which includes a tutorial for setting up and getting started, which is called Hello Cairo. First thing we need to do is use Python 3.7. It has to be Python 3.7. It doesn't work with 3.10, as I learned painfully. Then you follow the tutorial. That part is very easy. You create a virtual environment, and then you install the dependencies, which are ECDSA, fast ECDSA, and SymPy. Afterwards, you can install the Cairo language package, which includes the toolset, compiler, and a set of deployment tools. It takes a few minutes, a few seconds, depends on your computer speed and your internet connection. So that's not too bad. In the meantime, we create a Cairo directory where we can put our project files. Okay, so afterwards we can write the test program. So just copy paste the test program they have here. It's a function, it's a main, and I think it does 1000 plus 2000. Very low language here. You can see it's very close to assembly language. Seems actually even worse assembly language, since your expressions would be shorter if it was just a few instructions. But I guess it's for testing the low level language. Alright, so we compile and then we run. The output is just these three lines here: PC, AP, and FP, which are memory pointers. So the program binary takes 6 slots, and then you have you really have a stack-based machine. And, well, I'm not even sure it's stack-based, but you see the memory layout with the instructions, and then from 8 to 12 it's the memory segment. Alright, so I think that's not super easy to use. So the next step is to use the higher level language, which is Cairo. So first, this is all happening in the Goerli testnet, so not gonna use Bitcoin. So all this stuff is in alpha stage. So we can't use real coins. First, you need to deploy a wallet. So they have a test wallet. I already have deployed before, I think. That's why default is already created. And now, okay, this is the first contract really. So this is Cairo code. So what it says here is, well, there are a few functions. There are 2 functions: increase balance and get balance. And the storage variable. Storage variable is something that you can keep a state in between calls. Then you compile this stuff. That's like same as before. Okay, let's see it in the in Visual Code. Alright, so you can see that there is the balance storage variable and 2 functions: increase balance and get balance. There's a bunch of things like syscall PTR, mem_Pedersen PTR, and rencheck PTR, and I think you need to pass them because the function balance, which is used as a storage variable, implicitly depends on these guys. so they have to be part of the signature. And then yeah, once it's compiled, it creates the JSON file that has the contract API to the interface, the binary interface. Okay, yeah, that stuff. It's basically the input and outputs of each functions and the signature. Next one is we have to deploy the contract to the StarkNet network, which is Alpha Goerli. And once you have done that, it returns the contract address, and since deployment is also transaction, it also returns the transaction hash, which we don't really need, but we need the contract address. So then we can call a function using StarkNet invoke. So we want to call the increase balance function. So we have to update the call with the contract address, the function name, and the input parameters, which is like 1, 2, 3, 4. So this should increase the balance by 1,234. And then write down the output. This is the transaction hash. Really, the only thing that really matters here, because so this is going to be transmitted to the blockchain. Before it goes to the blockchain, it goes to peers. So the state of the transaction will be first received, and then it's going to be validated, and then eventually it's going to be accepted on L2. So this whole thing is on L2, right? Because we have set the network as being Alpha Goerli. So let me try to see if we can get the balance, call balance, get balance before the transaction is on L2. And I think it doesn't work. Yeah, it doesn't work. It actually says the contract is not deployed, which is a bit weird. I would expect it to say that the balance is 0 or some other error message, because the contract is deployed. We were successfully, well, we could successfully call into the increased balance. Well, I don't really know why. Yeah, it should really clearly say contract with address. That address, it seems to be in decimal. I don't know why they don't print it in hex as well, because it would not match the other hashes that are printed out. So it's still in receive status, and yeah, it doesn't seem to be very fast. It's been I don't know, maybe 30 seconds. Okay, now finally it's on L2, accepted on L2. So if I call the get balance, hopefully that should work this time. Yeah, it works this time. 1, 2, 3, 4. And now we can go to the next step of next part of the tutorial, which seems to be some other commands that you have on the tool, the deploy tool, StarkNet command. Alright, so we don't really need them at this point. It's interesting though, because I see now you can query the storage directly without running code. Okay, so what we can do now is extending the storage variable to be a hash map. So it would take a parameter. So everything that says failed is actually just an integer. It's like any a value, like a hash or something. So an address is also a hash. So it's a type failed. So now the storage variable is takes a parameter user address, which is a field, which integer, and still returns an integer with a balance. And other stuff that needs to change is when you increase the balance, you want to take the caller address, so that you increase the balance of that guy. And when you do the get balance, you also get the Well, actually, no, you don't get the caller address. You get a user, any user address, because it's okay to be querying balances of other people, since the entire state is not encrypted. It's not private. So in any case, you will be able to create the balance of any account. Okay. So this is a function to get a core address, and then the only thing we need to do is use that function to get the user, and then pass that when we do balance.read. And there's also check here for the amount has to be positive, but I'm gonna do it later. So just use the get address, and yeah, and then pass it in the argument of read. So user equal user. Okay, that's pretty simple. And again, in the get balance, we take argument user. Before there was no argument, but now we're going to take user address, and we're going to say we want the balance of that particular user. Okay. Alright, so now same stuff. We need to compile and then deploy. So every time we compile, the binary will be different, and we have different hash. So then the contract address will be different. Yeah, it's not the right name. The file was renamed to user auth.cairo. Okay, now we deploy, and then we should have the new contract address. So I'm going to copy the address and edit my notepad. Okay, so afterwards what we can do is call increase balance. Yeah. So this one we don't need to pass the user address, because it's by default going to be it's going to take it from the caller. So in that case, it's our account wallet address. Right? Boom, call this guy, and same thing again. The transaction is submitted, but we need to wait until it's included in the block. So this should return received like before. So now the trick is to find, so if we want to call the get balance, we have to pass an input parameter, right? The user account address. And my account was created with the deploy account command, which puts the address in and all the keys to some configuration file. So it's not super secure, of course, because the private key will be, but it's for development, and these are test coins anyways. Alright, so this is still not mine. It really takes a while to mine it. Yeah, it was. I'm looking for the account address. The documentation here, the tutorial here doesn't say how we get the account address, so it's something they probably should improve. Yeah, I'm looking for if there's a command in Starknet which gives the default account, but there's none. But if you Google, if you search a bit, you'll see that it's inside this directory, Starknet accounts. And there's a file here, a JSON file. which has private key, public key, and address. Of course, in normal case, you don't want to use this stuff because the private key is right there. Alright, so account address is this guy, and now we can go back to the command we had before and try the get balance command without account address. This is this guy here, and then I should need to replace contract address and account address. Alright, so now we can run this command, and we should get the 1, 2, 3, 4 that we had before. Okay. Alright, what else can we do? Okay, there's something about retrieving the revert reason. So that's related to error handling and getting messages and stuff. Alright, so for that, I'm gonna put back the assert, which is in Cairo file. So this assert here will assert that the amount that we pass in the increase is actually a positive number. Okay, so I'm looking for. Alright, he actually messed up. I just deploy. I changed the code and deploy, but you forgot to compile, so it's not gonna work. I mean, it's not gonna make any difference. Though. So in that case, yeah, I'll change the contract stuff. Same thing as before. But now I put a negative number, minus 1000, and I run this command. And same thing here, the transaction is submitted. So I take the hash and I use the transaction status command. And that should give me still the state received. And again, I have to wait a bit. Alright. What other features you have here? One interesting one is this interacting with L1 contracts. So this thing is running on L2, so it's not hitting the native blockchain of Ethereum, and so it's basically peers transmitting, changing the status between themselves, changing the state of the contracts, but it's not committed to the Ethereum blockchain. But what you can do is you can make a L1 contract, so a Solidity contract, which invokes things on L2, which calls a contract on Starknet, and vice versa. So what they describe is basically a pair of contracts, one on Ethereum and one on Starknet, which can communicate between each other. So that's fine. That's very interesting, and it's I'm going to take a look at that in the next video. So the example is a token bridge, which basically has a balance. It has a balance in L1, and for example, if you had if you buy some token if you have an exchange, and then you have some tokens on L1. So for example, Wrap ETH, ERC20. But then if you do transactions on Ethereum, it's fairly slow and also very expensive with the fees. So you would transfer these guys into L2. So you burn some L1 ETH, and then you mint some L2 ETH. Then you do all transactions on L2, which will be way cheaper. And then when you want to cash out, you do the reverse. Burning on L2, minting on L1, and then you can cash out. Alright, so yeah, it says accept on N2, which well, I was very surprised here because I was expecting the reject. But then again, it's because I forgot to compile. So yeah, if I call this, it gives him minus 1000. So it's not 1234 minus 1000, okay, which would be 234. It's because I redeploy the contract and then you reset the state. Alright, so now we compile. So I have command here. Okay, so yeah. Okay, it really helps if you compile. So we compile this time, and now we deploy. Okay, so one good sign that it was not compiled before is that we have an error now, and this error comes from the fact that the assert function was not declared. So we need to add this import statement. And now that should compile successfully. Then we can do the same stuff. Deploy. Grab the contract, the new contract address, and then call increase balance with this negative amount. And we expect to have, well, we expect the transaction to be received, but then rejected because it should not pass validation. Alright, so now we invoke, so the transaction is received, should be received, since we have transaction hash that we can use to monitor the status. And again, it's gonna take a while. Alright, so let's go back to this L1 to communication. So it says here that there's basically a command like send message to L1, which allows you to form any kind of message really, and then send it to L1 contract address. So the thing I don't really get is if you do that, who's gonna pay the fees? But I think it's still not completely polished, completely finalized. So it's still on alpha stage. And then you have L1 counterpart in Solidity, which then receives the message, right? And then this deposit is the opposite. So this L2 contract has the L1 handler, which handles a call from L1 to L2. So that was L2 to L1. And the L1 contract is classic Solidity. So the call for L2 to L1 is essentially just calling a method on L1. So the Solidity contract has really nothing very specific. Alright, so we can see the call was rejected, our increased balance was rejected, but we don't have really the reason, and that's because we did pass the source code, so the tool is not able to decode the exception address, and it's not able to give us a very precise error message. So now we use this extended version of tx status. Now we pass the contracts argument, and we're asking for the error message, and that gives us that the exception was raised in increased balance, and the message is amount must be positive, when it was raised by the assert. So this time it's fairly obvious what's going on here, and the number is out of range. It's kind of fun because the number is like very, very large, but I think that's just because felt numbers, when they are negative, they wrap around, yeah, that's just a very large unsigned number that matches the signed number. Okay, so that's it, and next time we will take a look at the L1 to L2 communication.